So Heisenberg proposed that even though an electron exhibits wave-particle duality, that we can't observe both its wave nature and particle nature at the same time. So what do we associate with the particle nature? Well, that would be the electron's position. And then once we know its position, we're at a loss in regards to its velocity, because the velocity would be part of the electron's wave nature. The reverse also holds true. So if we know the velocity, we're able to calculate that with some level of confidence, then we can just throw the position out the window. That's going to have a lot of uncertainty associated with it. We actually can calculate the magnitude of that uncertainty. The equation we're going to use, the Heisenberg Uncertainty Principle equation, is delta x times delta p is greater than or equal to Planck's constant divided by 4 pi. So a couple things here. This value over here is always going to be a constant. So if you're having any trouble at all plugging this into your calculator, or you're finding it annoying to plug in Planck's constant and do divide and all that, generate this value and you can use this same value for all the problems. Why I mention it as being slightly problematic is it's super critical that you put parentheses around the 4 pi. If there is an error, usually I can trace it back to that. So h, Planck's constant, divided by 4, and this is the pi, the 3.14. I'd actually just use the pi key on your calculator. For the units here, we're going to use those special units where we take, remember Planck's constant, joules times seconds, but we're going to plug in the definition of the joule. So at the end of the day, our units on this half of the equation will be kilograms times meters squared over seconds. But it comes from those original units, joules times seconds, with the substitution there. All right, so on this side of the equation, we have delta x, which refers to the uncertainty in the position. X is going to have units of meters. And then there's a couple other things to know about this. Depending on the wording of the problem, and I made some notes about that down here. Sometimes they give you a percentage and then they give you a speed or a position. Typically what happens is we know the uncertainty associated with one aspect and we have to solve for the uncertainty associated with the second component or second aspect. So that's why I wrote speed or position is given. We're going to do a problem here in just a second about someone caught in a speed trap. And so the police officer, in theory, right, is using a speed gun to calculate the speed of the moving vehicle. Whatever instrument you use in the lab or whatever instrument you're using anywhere, right, whether it be a speed gun or an instrument in the lab or a ruler at home, whatever it is, there's always going to be some level of inaccuracy associated with that. It's called uncertainty. And so a lot of times, especially with equipment that has to hold up in court or for scientific review, they tell you what is the uncertainty associated with that equipment. And so that's often expressed as a percentage. So in my scenario here, we have police officers using that speed gun and they know that it has 1% error, or maybe they have a really cheap speed gun and it has 10% error or 10% uncertainty associated with it. So if they give you a speed, an outright speed, and then they give you the uncertainty as a percentage, the uncertainty associated with that device or instrument, then we need to multiply those two things together. And I wrote percent divided by 100 because we want to convert that percentage to decimal form. This is all going to probably make a little bit more sense when we jump into the problem, but why I'm bringing up all this detail right now is because sometimes when I see delta x or delta V, we'll do that in a second, I think of this as percentage times my position. So the delta being the uncertainty part. Where it actually comes from, though, is calculus. So since this is a non-calc course, we can't have you do any integrals or derivatives, but this actually means dx. So if you're familiar with calculus, if that's something you enjoy, then you know where that's coming from. We're substituting in delta for d. Uncertainty of momentum can also be rewritten. Momentum is mass, but since it's an uncertainty associated with the momentum, we're going to do delta P equals mass times delta V. For mass, so in the example that we're going to do with the car, that's going to be the mass of the car. So if you have a problem about an electron, and we're not going to limit our problems to just electrons, right? Because wave-particle duality says, well, if something applies to a photon, an electron, and really small things, where is the cutoff between quantum chemistry and more classical models? So we can look at this for any kind, subatomic to macroscopic particles. So we have mass, the mass of the object. That's going to be in kilograms. And then we have this delta V, which in some cases is going to be the percentage times the velocity, the uncertainty times the velocity. But those units have to be meters per second for that. This is arguably the most important problem of the course, especially if you're a person who gets a lot of speeding tickets. So think about what Heisenberg said. Heisenberg said that if we know the position of an object, then we don't know its speed. And if we know its speed, then we don't know its position. So if a cop is standing there with a radar gun and pings you at 100 miles per hour, then according to Heisenberg, they don't know your position. So how do they really even know that it's you, right? If you know my speed, then there's no way you knew it was me. And if you knew it was me, then there's no way you knew my speed. So let's see. So somebody's going 90 kilometers per hour. And then they're in a very small car, probably like a European car, right? It has a mass of 1,250 kilograms. So let's see if this argument will hold up. Let's actually crunch the numbers and see, well, if that speed gun has an uncertainty of 1%, and that's pretty reasonable, right? What would be the uncertainty with the position of the car? Would that be enough to argue, well, you knew my speed, therefore you don't know it was really me. You don't know my position. Like when they report I always think about when they report like the mile marker, right? Then you don't know where I was. All right, so first things first, uncertainty in the position. What do they want from us? So this phrase right here tells us that they want us to solve for delta x. We're not given delta v directly. We have that scenario where we have to take the speed and multiply by the percent. However, before I even do that, I'm a little bit concerned because this is kilometers per hour and we need meters per second. So let's do that conversion first before we even start multiplying. So 90 kilometers per hour, 1 hour has 3,600 seconds, and 1 kilometer has 1,000 meters. All right, what's canceling? Kilometers with kilometers, hours with hours, and I'm left with meters per second. So when I did that earlier, I got 25 meters per second as my velocity or speed. Delta V is going to be 0.01. So I took this 1% and I just moved the decimal place over or converted it to a decimal form. So just divide by 100. So I'm going to do 0.01 times the 25 meters per second. So I'll leave it like that. I actually plugged it in all in one step, so I don't have that number written down. So let's do the calculation then. We have delta x times mass times delta v is greater than or equal to Planck's constant over 4 pi. So I'm asked to solve for delta x, so I'll divide this side by mass times delta v. And I'll do the same over here. So now I have delta x equals h over 4 pi divided by mass times delta v. Let's plug in some actual values. So Planck's constant, the 6.626 times 10 to the negative 34. I'm using these manipulated units because I want to see how stuff cancels. I don't want to leave it as joules. And then 4 pi, that's something that I just make sure you get those parentheses. But that's something that I just plug into my calculator, just like that. And then divide it by, I usually plug this all in one step, but you could definitely do it in 2 steps. I would do the top here and then hit enter if you're going to do it in 2 steps. Hit this enter, which will give you the big set of parentheses here, and then you're going to divide by, use another set of parentheses. Our mass was 1,250 kilograms, and then our uncertainty was 0.01, and I want to multiply that by my velocity, so my 25 meters per second. What's canceling? Let's see, kilograms is going to cancel kilograms, seconds with seconds, and one of the meters is going to go away, just leaving us with meters. And that's perfect for an uncertainty in position. When I did all this, I got delta x is greater than or equal to 1.69 times 10 to the negative 37 meters. I figured I'd just round to 1 sig fig because of the 1% here. Also, the greater than or equal than sign almost kind of makes the sig figs irrelevant, right? So it's only like an estimate of your uncertainty. But we could pretty much say delta x is greater than or equal to 2 times 10 to the negative 37 meters. About 1 sig fig. All right, so what's the consequence of that? First off, if bring a whiteboard into court, do all this, you probably put them to sleep, they probably let you go. But on the other hand, if someone follows you through the end of the problem, right, they're going to look at this number and say, damn, that's a really small number, right? We talked about the length of a bond and an atom and stuff like that, and it's nowhere near this small, right? This is beyond small. So this uncertainty, like, yeah, the cop knows where you are because the uncertainty is so small. And this is what we see for larger objects. That once again, that theme that the quantum approach is not appropriate for macroscopic objects, for things that we can see. We saw that with the de Broglie wavelength equation too. But our next problem will be about a microscopic object, and then we're going to see why Heisenberg's proposal was so important. But yeah, this is far-fetched. Yeah, they know where you were at. Alrighty, so this time we're asked to solve for the uncertainty in position associated with an electron. So this is what I noted here, that we want to solve for delta x. Let's start with Planck's equation. So Planck's equation is delta x, the uncertainty in position, times delta momentum, but I'm going to break down that delta p into mass times delta v, and that's going to be greater than or equal to h over 4 pi. I'm going to divide both sides by mass times delta v so I can isolate delta x. Cancels out over here. So now I have delta x is greater than or equal to h over 4 pi divided by mass times delta v. Just adding in all those parentheses that you need to make sure you use if you're trying to plug it in all in one step in your calculator. So we have Planck's constant 6.626 times 10 to the negative 34 kilograms times meters squared over seconds. That's all going to be divided by 4 times pi. This whole term, which in and of itself is a constant, that's going to be divided by the mass of the electron, which is already in kilograms for us, times the speed of the electron, which already has the correct units. We need meters per second, times the delta part, the uncertainty part. So it's 10%. So I want to multiply by 0.10. Sorry, that was kind of in there in a different order, not wrong, right? But just this right here is the 10%. And so we have the velocity, the known velocity times the uncertainty in the velocity. All right, so put all that in your calculator, and we get a delta x value of, so the uncertainty is greater than or equal to 2.6 times 10 to the negative 10 meters. I left it at 2 sig figs. I just, maybe 1, I don't know, it's arguable. I just said maybe that's exactly 10. Just do that. It could be 1. You could argue either way. They wanted this in picometers. We haven't seen too much of picometers, but just another metric conversion factor. So that would be 1 meter has 1 times 10 to the 12 picometers. So when I multiply the original answer by 1 times 10 to the 12, I got 260 picometers. And again, if you want to say, oh, I just want to say about 300 picometers, that's fine as well, either or. In the last problem that we did involving the car that was speeding, we reached the conclusion that the delta x was so small that it's a ridiculous argument to say that the position was unknown. Now we're dealing with an electron, something that actually follows quantum models because it's so small and so fast. What is the significance of this uncertainty? Well, I looked up the hydrogen-hydrogen bond length. So diatomic hydrogen, right? Hydrogen gas, so H2. And we always draw it, you know, just bond it to another hydrogen. So the distance between these two hydrogens is around 74 picometers. This problem deals with an electron in a hydrogen atom. The questionable part about its position is 300 picometers. So think about that, right? If this distance is 74 picometers, and the uncertainty is around 300 picometers, then the electron, right, we don't know where it is. It could be anywhere in this huge area. The uncertainty is larger than the distance between two hydrogen bonds. So, I mean, and what's the probability that the electron will be out here? Well, that's a whole different calculation and argument, but we really don't have a clue where that electron is. And I'm sorry, I'm getting very excited about it. We're going to go into orbitals in our next section, and you'll see that they really don't know, that it's all just based off of the probability of finding that electron, but we don't really know where the electrons are. So another problem about an electron, the wording here is a little bit different. It says the uncertainty in its position is 552 picometers. That means somebody's already maybe multiplied that percentage times the position. So I'm going to interpret this to mean this value right here is my delta x. What is the uncertainty in its velocity? So this time we're solving for delta v. I went ahead and converted the picometers to meters, and then I also did the manipulation on the Heisenberg Uncertainty Principle equation. So let me start plugging in all my numbers then. I have 6.626 times 10 to the negative 34 kilograms times meters squared over seconds divided by 4 times pi. They didn't give me mass here, but the mass of an electron is constant. I'm going to grab the one from the previous one. The previous problem, they told us it was 9.11 times 10 to the negative 31 kilograms. And I'm going to just use this value. Again, this value equals delta x. So no extra multiplication step because of that wording. So crunch all those numbers. Let's see, kilograms cancel in kilograms. One of the meters goes away, and we're left with meters per second, which is perfect because this time we are solving for velocity. And so if we know that position to that level of detail, then the velocity is going to be questionable to about 1.0 times 10 to the 5th meters per second. So the uncertainty with the velocity is greater than 1.0 times 10 to the 5th.